This is my lab 3 on circuits for Physics 2212 by Elias Grimmelman. The contents of this lab will be the introduction showcasing the purpose of the experiment and concepts, and the two parts of the lab, which are part 1, charge conservation and energy, which is the conservation of energy in series circuits, and part 2, the time-dependent voltage across a discharging capacitor. This lab experiment will explore series and parallel circuits containing resistors and capacitors and measure currents and potential differences using ammeters and voltmeters respectively. The concepts and formula for this lab are the node rule, which states current in equals current out, the loop rule, which states that the sum of the voltage in a series will equal 0, and the potential difference across a capacitor, which was rearranged for this lab in order to find time-dependent voltage over a discharging capacitor. Additionally, Ohm's law will be used, which states that voltage equals current times resistance. These are the diagrams for the first part of the lab that state that the current does not change through a resistor, and if an ammeter is reversed, it will still equal the same current, but just be negative because the leads are changed. If you replace the ammeter with a voltmeter, then the current turns to 0 because there is no connection between a circuit, and it is not closed, but a potential difference still exists due to the batteries in the circuit. When looking at the potential differences in a series circuit, they do not change across a wire, they only change across resistors and batteries. So for the 47 ohm resistor, the voltage decreased by 0.959, and for the 100 ohm resistor, the voltage decreased by 0.2041, and increased by 3 volts at the location of the batteries. But across the ammeter and other parts of the circuit, the voltage stayed the same. When an ammeter is placed parallel to the 100 ohm resistor, the current read by each ammeter was 0.06 amps. This is because the current was split instead of all going through the resistor. When a voltmeter was replaced with the ammeter still read 0.02 amps. The observation that was made states that the voltmeter did not affect the current because it had a very high resistance and there's very little current flowing through it. So it is as if the current never even split, and their ammeter reads the same amount. The resistance for each of the following parts of the circuit, according to Ohm's law, was 47.95 ohms for the 47 ohm resistor, 102.05 ohms for the 100 ohm resistor, 0 for the wire, and 0 ohms for the ammeter, since those do not have any resistance. When charging the capacitor, the light starts bright, but dims as the capacitor is fully charged, and then the current stops. When discharging the capacitor, the light turns on as the current flows until the capacitor runs out of charge. The current stops and the light goes dim once again when the capacitor runs out of charge. The effect of the resistance on the charge in discharge of the capacitor was that the 10 ohm bulb would take about 9.7 seconds to charge and 9.9 seconds to discharge, whereas the 20 ohm bulb would take about 19.4 seconds to charge and 19.7 seconds to discharge. It takes a 20 ohm bulb approximately twice as much time to charge and discharge than a 10 ohm bulb. The time-dependent voltage across the capacitor was calculated by finding the time constant using the potential difference across the capacitor at various points in time, and using the equation in the introduction. The time constant is the time for the voltage of the capacitor to decrease 1 over E of its original value. The time constant for this lab was 5.9418 seconds, which was calculated by graphing the natural log of the voltage over the original voltage versus time and finding the slope. For the discussion questions, if an ammeter in real life was used instead of an ideal simulated ammeter, the current measured would be lower since a real ammeter has a slight resistance, whereas the ideal does not. If the lab was done in real life, the capacitor would most likely take a longer time to reach full charge, since all components in reality have resistance to them. The ideal model shows no resistance for simplicity. The conclusion for this lab states that the sum of the potential difference in a circuit sums up to be 0 volts. The time constant of the given circuit in this lab is 5.9418 seconds for the voltage across a discharging capacitor. The lab helped determine the behavior of circuits and the way they act in parallel and series, along with how resistors affect current and create potential difference, and how capacitors can be charged and the rate at which they release current.